So then our first speaker of the session is Chowdhury, and he's going to tell us about solving the decades-long mystery of Saturn's planetary period oscillations using Keck-NIRSPEC. Okay, so if you're ready, go ahead. I'll give you a 2-minute warning by flashing the 2-minute warning sign.
Sounds good. Thank you ever so much. Yes, hello everyone. My name is Nahid. I am a teaching fellow in physics at the University of Leicester in the UK. I'm wearing black trousers, light blue shirt, a light blue tie. I wear glasses, I have black hair, and behind me I have a row of books, mainly mathematics and physics textbooks. And yes, I'm going to be talking to you today about some work that I carried out during my doctorate degree, excuse me. It's a piece of work that was published around about December of last year. Here we go. This is the structure of my talk. I'm sure it's not a surprise that I'll be beginning with the introduction, followed by a look at the methodology before exploring some of the results. Okay. So, introduction, planetary period oscillations. For those of you who are unfamiliar with Saturn, there is a very peculiar behavior that we observe at the ringed planet. Basically, Saturn's magnetosphere is filled with oscillations that have a period which is close to the rotation rate of the planet, around about 10 hours and 45 minutes or so. And these perturbations, these oscillations are observed in numerous parameters, such as the aurora, such as electron data, magnetic field data, and so on. And collectively, they're known as the planetary period oscillations, or PPOs for short. Okay, so I've included a short fact file here about Saturn. I'm sure you know that its distance from the sun is just under 10 astronomical units. It has an orbital period of almost 30 years and an equatorial radius of around about 60,000 kilometers. Okay, let me talk to you about the Cassini mission. So the Cassini mission, NASA's Cassini mission, really revolutionized our knowledge of the periodicities using its many instruments. For example, the Radio and Plasma Wave Sciences instrument, RPWS, was the first one which gave a measurement of Saturn's radio period in the Cassini era. And this was around about 10.76 hours by the remarkable Don Garnett, my apologies. Further analysis over the years was then able to firmly establish the presence of two separate kilometric radiation periods at Saturn, which exist at the same time. So you have one period in the northern hemisphere and one in the southern. So yeah, the plot thickens basically. But anyway, here are some snapshots of some of the results from or summarized by Chowdhury et al. We've got the two radio period measurements, one from Voyager 1 and 2 back in the 80s, and then the second from the Cassini spacecraft. And you can see that there's been a slight change in this radio period, a difference of about 6 minutes. And really, we don't know what causes that difference, or at least we didn't know for a long time. And then here's an example of these, the periodicities in the northern Saturn kilometric radiation, which is the radio emission, and then the southern as well. And you can see the total SKR in that top panel there. So generally speaking, we're looking at a period of around about 10.6 hours in the northern SKR, and it's around about 10.8 hours in the southern. So two independent periods there. Okay, so what causes these different periodicities, these perturbations in rotation period? So people have come up with a number of theories, but mainly there are two schools of thought. One is that there is a mechanism of some description driving these periodicities from outside of the planet, so a source in the magnetosphere. And the other school of thought suggests that actually this source, which is driving the periodicities, exists within the planet's interior, more specifically, actually, in its upper atmosphere. So the data that we had from Keck-NIRSPEC, it meant that really we were able to test the theory related to the source being in the atmosphere of the planet. And what we were doing essentially was comparing the model predictions from authors such as Gia and Smith, and indeed some of the predictions made by Hunt in these diagrams with the observational data that we have available to us. So I'm not going to go into too much detail about this figure. It basically shows you the magnetic field lines at Saturn, and of course some of the planetary period currents, which are thought to be responsible for the periodicities that we observe. Okay, right, let's have a look at the methodology then. So the data that I'm using, it came from 2017. My principal supervisor, Thomas Stallard, went to Hawaii over the course of the summer. So this is summer in the Northern Hemisphere of 2017. And there were a total of around about 7 nights of observations that he carried out using Keck-NIRSPEC of Saturn's northern aurora. So this is a page from a piece of work that he published in the first instance about this data, about these data, I should say, and just outlining the different dates. So we started in July all the way through to August, and the dates were sort of spread out over that period. So over the course of a month, essentially. And really, the aim was just to scan the northern polar region of Saturn using the instrument SLIT. And these observations actually took place around about the same time as the Cassini grand finale orbits. So here's another image from his earlier work published with the Royal Society. So you can see the instrument SLIT of NIRSPEC there trained on the northern polar region of Saturn. And as you step the slit down and take an exposure each time, you can produce a map essentially. And this figure here, or at least this part, this right-hand side, you can see the reflected sunlight from the rings, sort of down the sides. And in the middle, you can see the emission line of H3+, which is an ion, a hydrogen ion in the upper atmospheres of gas giant planets, which we use to probe the dynamics of the aurora. And here's a spectrum, or a specs. I guess this is order 19 and order 21 on the output array of Keck-NIRSPEC, and you can see the 2 emission lines highlighted. There's the Q10 emission line of H3+, which is very bright compared with the R22- emission line, which is a little less strong, but still important because we can use it to derive temperatures. Right then, so we have these raw spectral data. How do we go from spectrum to an image of the planet? Well, it's a non-trivial process, and unfortunately I don't have time to go through the nitty-gritty of it all. But what I'll tell you is you can go from these spectra, very plain spectra, into an image of the planet. So what I've got here are images created from the different spectra that we have for each of the nights in order 19, essentially. And you can see that, for example, at the top there in the middle, that data was collected using the slightly wider slit, 0.288 arc seconds, but then some of the lower images illustrate the result when you use the slightly thinner slit. Sorry, I've got that the wrong way around. The wider slit is 0.432 arc seconds, and the thinner one is 0.288 arc seconds. Okay. The other thing we did was we binned the data into quadrants of northern magnetic phase. Okay, and these tables and this diagram here, they illustrate the number of spectra that we ended up putting into each of these quadrants. You can see that there's a fairly good coverage in most of them, except for the quadrant that was centered on 180 degrees. There's only about 80 spectra compared with the 3 figures in the other ones. And what this would allow us to do is basically explore the ion flows of H3 plus when they're fixed to the planetary magnetic phase. Okay, on to the results with just about 2.5 or so minutes to go. Let's have a look. So I've got 4 quadrants, and because they are fixed in the phase of the planetary period, what that means is I can subtract one from the other to isolate the ion perturbations which are associated with the planetary period current. Okay, so hopefully it should allow us to see whether there's a source in the atmosphere which is driving the periodicities that we observe. Just before we do that though, here are the emission intensity maps along the top, the line of sight velocities of the H3 plus ions, and the average profiles along the bottom for each of the 4 quadrants that we had. Yeah, I'm just going to skip this briefly and show you the next slide, which is really where all the action happens. So if we take the quadrants which are of opposing phases, essentially, subtract one from the other, we can isolate the emission and then create a map of the ion flows, which is what I've done here. Okay, so just zoom into it there. At the top, we've got the modeled ion flows based on a driver bay within the magnetosphere. And then in the middle panel, we've got the ion flows or predicted ion flows based on a driving source, which is in the atmosphere. And then there are our observations right at the bottom there. And in fact, you can see that our observations match up rather well with the predictions from the thermosphere, as in there's a source driving the periodicities from the thermosphere of Saturn. Okay, that's a very clear-cut result, and yeah, it was absolutely amazing when it just sort of jumped out at us. I remember my supervisor saying at the time, you know, Nahid, there's only 2 people in the world that know the answer to the question, and it's only, yeah, it's the 2 of us basically. So yeah, that's all I had for you. Thank you very much.
Questions are here.
I don't see anything else left.
John has a question.
Where else in the solar system might you want to do this?
That's a good question. So I guess the easiest target is Jupiter, because Jupiter's H3 plus emission is strong enough to be able to be detected by what we have currently available to us. Beyond that, I guess if we make use of JWST, we can possibly carry out the same experiment at Uranus potentially. And if we get even better equipment, then potentially exoplanets.
Bruce, and thinking about observations like this in future Keck capabilities, you know, one of the new incoming instruments is scale, which will be a 2 to 5 micron integral field spectrograph. Would that make life easier to have a full image instead of having to march a slit around, or in the end you've solved all the slit marching problems?
Yeah, that's an interesting point, because the way it is, the techniques we've used have been well developed over the course of several years, more than a decade. So at the minute, we're quite comfortable with the way we're doing things. That's not to say that we wouldn't be against, you know, having better tech and possibly making our lives a little bit easier. But yeah, it's a tricky one for me personally. I'm fairly happy with how it is, but I'm sure, you know, when there's something new that comes along, you always want to yeah, be a part of that buzz. Certainly.
Great. Other questions? All right. If not, let's thank our speaker again.